Hello everyone, the next speaker is Benjamin Peterson, and his talk is titled The Slightly Less Sorry State of SSL. So please give him a warm welcome.
Thank you very much, everyone, and good afternoon. As he said, I'm Benjamin Peterson. I'd like to tell you about SSL and Python. But first, let me look at the program here. Okay, so what am I up against? Raymond Hettinger, Beyond PEP 8, the best practice for beautiful, intelligible code. Okay, nothing is going to be beautiful in this talk, so maybe you should go to that. Inside the Hat, Python at Walt Disney Animation Studios. Now that one you should definitely go to because it's not being recorded due to all the cool graphics which are being shown. So that's in 517D. It's downstairs. I was watching it in the speakers lounge. It looked really good. And let's see, HTTP2. Well, I guess that uses SSL, so maybe you can just watch that later. All right. So as you can see in the program, the talk is listed as a dive into TLS. And the title here is a bit different. And the reason for that is that when the talks were accepted, I noticed that there was a talk which overlapped a lot with my original proposal, specifically describing the actual TLS protocol. And additionally, in the time since talk proposals were due in September, a lot of interesting things have happened in the Python SSL module, which I'd like to tell you about. So I'm going to be talking about improvements made to the Python standard library SSL module over the last year. And remember, Paul's talk is downstairs. All right, so as I said, I'm Benjamin Peterson. I have been a core developer of CPython for about 7 years now. And I've worked on a lot of different parts of core Python language and the standard library. And I've also been a release manager. And the other thing which you may know me from is writing the 6 Python 2 and 3 compatibility library, which I hope has helped you adopt Python 3. Okay, so that's enough boring things about me. Let's talk about someone much more interesting. So this is Hinek Slavak. As you can see, he's a very cool guy because he has this picture on his website of him staring out at blackness. He's sitting in the front row if you want to meet him. And so last year, Hinek gave a talk at PyCon, Montreal, and also a few other places, called The Sorry State of SSL. And as you can see, my talk title has been derived from his. And as you may surmise from the talk title, he was basically pointing out all the terrible things in the Python community which surrounding the support of SSL. So later in the talk, he also had this slide, which, ouch, that kind of hurts, that burns. And so my hope is to explain to you, remind you why Hinek says we were at the forefront of terrible, and then convince you that we're slightly ahead of the forefront of terrible. Okay, so again, why are we so sorry about the state of SSL in Python? So let me begin by reminding you about the standard library SSL module, which is the main topic of this talk. So it was added in Python 2.6, which I remember, but as far as technology is concerned, is basically ancient history. And its basic operation is that it's a wrapper over OpenSSL. So there's no code in CPython which actually knows how to speak the TLS or SSL protocols over the wire. That's all handled by OpenSSL, and the SSL module just uses the C OpenSSL APIs. So that's good both because we don't have to maintain a TLS implementation in the standard library, and bad because every time there's an OpenSSL CVE, then all Python stuff is screwed over. And the API of the SSL module is basically a fake socket API, at least the traditional API. And so what that means is that you would make a raw TCP socket, and then you would hand it to the SSL module, and you would say, wrap this socket with TLS, and then OpenSSL would speak TLS or SSL over the TCP socket which you created, and you interact with this with APIs which are exactly like the raw socket APIs. Like you say, write 25 bytes or read several bytes. And so this made it somewhat easy to just add TLS to a raw socket protocol when the API works. The abstraction breaks down sometimes. And the other important thing about the SSL module is that it is what provides HTTPS support in the rest of the standard library. So in particular, httplib, because HTTP and HTTPS protocols are so important in modern computing. But also, if you want to do XML RPC over SSL, the standard library will use the SSL module for that. So it's, in a way, it's the canonical source of SSL support for Python. And the other thing which needs to be noted is that the SSL module saw many improvements in Python 3, and 2.7 was basically left behind. And so we're going to see how that created a bit of tension. So more or less what happened is Python 2.7 was released in 2010. And this is going to be the end of the 2.7 series, the last major release. All new features are now developed on Python 3 branch. But that also means that the SSL module in 2.7 was frozen in 2010, and unfortunately, a lot of the modern APIs which you need to do modern, secure cryptography and TLS are absent in the 2.7 version of SSL, even though they were present in Python 3. And so they were not accessible to the large number of Python users who are still using Python 2.7, and they are more or less being left in the dust to fend themselves in terms of SSL support. Specifically, some of the important things which were missing was support for the newer protocols in TLS, TLS 1.1 and TLS 1.2. And that's bad not only because TLS 1.1 and TLS 1.2 are newer versions of the protocol with some security improvements, but also because TLS 1.1 and 1.2 are required for modern cipher suites. The kinds of ciphers which we want to be using today are just not available in TLS 1.0. And so if you don't actually have the ability to support TLS 1.1 or 1.2, then you're kind of stuck with these older, often broken ciphers. In particular, you don't have the important ciphers which have important properties like perfect forward security. There's also just missing features from the SSL module which are needed in modern networking applications like next protocol negotiation, which is a TLS extension used to negotiate the next application layer protocol. And what this really means is that it's used to negotiate HTTP2. And since HTTP2 has been finally standardized now, this has become a much more important issue. And another similar thing was server name indication, which is a way to host SSL or TLS services as virtual hosts. This is needed to do that. And then the final thing was that there was no built-in way to access the system store of certificates, and you had to build your own code for that, which on Unix systems, you just usually have to search in the right locations to find the certificate store, but on Windows, you actually have to, there's custom Win32 API code, which you have to write to access the system store. And the final thing was that in 2.7, there were just bad defaults, which we know are very dangerous in security-sensitive code in API design in general, of course. So, as I said, like all the protocols were allowed by default, so completely insecure protocols like SSL3 or something, you know, it would just be used by default unless you turn it off. And the cipher string was the one which was used by OpenSSL by default, and that included a lot of insecure ciphers. This is like the sort of way that the TLS export ciphers would get added, and that's how that sort of thing would happen. And then there was no certificate trust verification by default. They would just accept any, clients would just accept any cert which was handed over, and there was no hostname validation by default. So the sum total of all this is this very innocent line. Just using standard library networking code, import urlib open, the HTTPS version of the Python.org website was completely insecure. It's as bad as using it over HTTP because there's no certificate validation or hostname validation. And in fact, it's quite a bit more insidious because people think that they're getting security by putting an S there, but the standard library was not guaranteeing that at all. So I would like to report on the progress over the last year. And this comes in the form of two PEPs. The first one is 466, Network Security Enhancements for Python 2.7.x. As the name suggests, this involves adding a whole lot more security features to the SSL module in Python 2. So what you can think of is that the 3.4 SSL module is just backported to 2.7. And that's actually essentially how the backport, this PEP was implemented, was backporting and porting everything back to 2.7. So this was rather exceptional because we have a very, in core CPython, we have a very strict backwards compatibility policy, which says that we should not add new features to bug fix versions of releases. But it was felt that we were getting to the point that we were leaving Python 2.7 users with this totally insecure SSL module, which wasn't appropriate in the modern world that we live in. So the things this backport included are the SSL Context class, which I'm going to talk about briefly at the end of the talk, and also the ability to support newer versions of TLS with the associated good ciphers and server name indication. And then there were a few tiny other things which were backported from Python 3 to other modules, namely PBKDF2, which is a key derivation algorithm, which is now in hashlib, which is what you should use when you get a password and you're going to put in your database. You shouldn't use SHA-1, you shouldn't use SHA-512 with assault, you should use one of these key derivation algorithms. And then there's also a constant time comparison algorithm for comparing the hashes, which to prevent timing attacks, and a few other things. And then the second PEP, which came out, was 476. The name is pretty self-explanatory. Enabling certificate verification by default for standard library HTTP clients. So what this meant was that httplib and its consumers would verify certificates, do trust verification by using the system certificate store by default, and do hostname verification. So it should be roughly on par with what your browser does, although your browser has a lot of other features. But this is, so probably we're actually providing actual security by default now. And so this was released in Python 2.7.9 and 3.4.1, which came out, 2.7.9 came out December, and 3.4.1 came out in February, I think. So this is somewhat new, but if you're able to upgrade your Python, you'll be able to take advantage of these security improvements. And additionally, you're able to configure the TLS configuration of standard library protocols if you don't want to use the default by passing a context argument to, for example, httplib or XML RPC lib. So let me briefly elucidate a few of the things which were backported to 2.7. So one of the main things was this class called SSL Context, which is in the SSL module, which basically serves as the configuration for an SSL connection. All of the arguments which you need to make an SSL connection. And this replaces the original API in the SSL module called wrap socket, which it has like 12 arguments and still needed more. And so now they're all wrapped up in this class called SSL Context. And so among the configuration things are the certificates which you want to trust, whether hostname verification is enabled, the cipher strings which you're willing to negotiate, and the protocols which you're willing to speak. So that's SSL 3.0 or TLS 1 or TLS 1.2. And there's a whole lot of OpenSSL flags which you can add or remove at your leisure to configure fun OpenSSL behavior. And so this is the thing which I said that many networking APIs now accept, the SSL context. So you can pass an SSL context to httplib, and it'll use that configuration to make HTTPS connections. So you can instantiate your own SSL context. You just get a blank one and then do whatever you need to do to configure it. But you shouldn't do that. You should use this function called create default context. And what create default context does is it makes you an SSL context with good defaults. And so this is the one which is used throughout the standard library. And so if you need to tweak something, you can create a default context and then just tweak whatever you need, and all the other defaults should be good. So in particular, we have a good cipher string with good prioritization using some of the newer high-quality ciphers, which was actually suggested by Hinnick. And we also load the system certs to do trust validation. And the best thing is that now we'll be able to update this function as TLS best practices evolve, and make sure that everything stays secure. For example, we just recently removed the cipher RC4 from the default protocol string because there's an RFC which says that you should not use it because it's broken. There's some pretty cool bias attacks. And so, as I said, create default context is the one which is used by the standard library networking. And then, so as I alluded to before, we now have support for several more TLS extensions to the protocol, which are important for modern networking. Specifically, server name indication, which allows for virtual hosting to work with SSL. And also next protocol negotiation and application layer protocol negotiation, which were both were suggested by Google in order to allow the negotiation of speedy and now HTTP 2. But in theory, you could use it to negotiate whatever the next, any protocol that you want. And there's custom hooks in the SSL module which let you say, I would like to speak protocol gobbledygook instead of HTTP 2. And if the server supports it, then you should be able to switch seamlessly to that. The last sort of more advanced feature which I'd like to talk about, which is not actually in 2.7 because it's even newer than 3.4, is memory BIO support. So as I said at the beginning of talk, one of the SSL module provides this socket-like API, which just sort of pretends to be a raw socket and then speaks SSL over the underlying raw socket. But sometimes it's useful to be able to separate the actual I/O from speaking the SSL protocol. So this is what memory BIO allows you to do. So you write a bunch of bytes to a buffer, and then you say, SSL, turn this into OpenSSL, turn this into a SSL protocol frame or something. And then SSL gives that back to you, and it doesn't send it on a network anything, and then you can send that however you would like to. So this is mostly useful for higher level frameworks like async IO, and Twisted has been doing something like this using PySSL, which has had support for this longer. And as I said, it's only in Python 3.5. Okay. So I hope you think that we're not at the forefront of terrible anymore. The happy thing about this is that there's usually somebody who's worse than you. Ruby. Okay. And I'd also like to put in a plug for requests, which has been doing stuff like this for much longer than it's been done properly in the standard library, and is just generally a very nice API for making HTTP requests. So use requests, and everything will be all right. All right. Finally, I'd like to personally thank a lot of people who made these things possible and vastly improved the security of Python. Particularly Alex Gaynor and David Reed did a lot of the backporting work, which was a massive task, thousands of lines of C code. And Nick Coughlin and Donald Stuft wrote a lot of the PEPs, and other people helped with reviewing code, and there's a lot of people who aren't named here, but I'd like to personally thank them. And with that, hit me with questions. And thank you for coming and not going to Paul's turn.
So we've got a few minutes for questions. If you've got one, please step forward and come to the microphone.
Hi, Benjamin. Thank you. I'm Trishang from the Duff project. So my question is, how often would you update the standard lib as you find new, say, ciphers that shouldn't be used? Yeah. Does that mean you'd have to release a new version of Python?
Yeah. So, I mean, as soon as it seems like there's cryptographic consensus in the security community that we should not be doing some particular thing, then usually, especially in the case of ciphers, it's not very hard to change the cipher string. In some cases, there's issues of compatibility. Like the big thing with RC4 has been known to be weak for a very long time, but it's like the only sort of secure protocol which Windows XP could speak, or Internet Explorer 8 on Windows XP, which has, I mean, it's still on, for example, Google and other popular sites because they feel that they need to support Windows 8. But it's not too hard to update most things, and then that'll just come in the next bug fix release if we think it's warranted.
You mentioned offhandedly that there's a special key derivation function that we're supposed to use for hashing passwords in place of using something out of hashlib. So could you talk a little bit more about that and what that is and why that's a good idea?
Yeah, sure. So it's actually in hashlib now, and it does not have a very good name, PBKDF2. Yes, Hinnick is nodding. Okay. So just take the obscurest one and pass passwords to it, right? Yeah, so hashing obviously is a good start, but what these key derivation functions do is that they try to ensure that deriving the password takes substantial resources. So if you're just hashing one password, it's okay if it takes 10 milliseconds or something because you're only doing one. But if you're trying to break passwords and you're trying to create these rainbow tables, these giant tables of common passwords, then even a function which takes a few milliseconds can really slow down hashing billions and billions of strings. And so there's other competing functions like scrypt, but they're all pretty good. And so that's considered to be the modern standard in password hashing, if that makes sense.
Thank you.
No more queries? All right. Thank you again.